I'm Steve McLaughlin, Dean of the Georgia Tech College of Engineering, and this is The Uncommon Engineer.
Fine. 1-800. We live in an age.
Sounds incredibly complex. It sounds like students, you need to have abilities that span. I'm really geeking out here. Maybe you could say a little bit about carbon nanotubes and then how those fit into your research.
I'm a carbon nanotube fanatic, if there ever was one. It's the reason that I went to grad school. It's so the carbon nanotube. I'm from Pensacola, Florida, and I grew up. I tell people I could run to the Alabama border, so it's not Miami. It's lower Alabama. So you get very familiar with chicken wire, right? So if you think of chicken wire, the honeycomb structure. That's what the atomic structure of a carbon nanotube looks like, rolled up like a cylinder. And it's important because if a very simple way for just people in public to think about what makes something a good conductor of heat, the lighter the atoms are and the stronger the bonds, the more efficiently the energy transfers. Carbon-carbon bond is strong. We know that's one of the strongest. And then the carbon atom is light. And so this carbon nanotube is important because it's frankly the end game for how fast heat will transfer in a material. And researchers have just been at it for decades now. The material was first discovered in 1991, and researchers have been trying to take advantage of its properties to do things, not just in heat. The material is 10 times stronger than steel at 10 times smaller diameter. So it's strong, it's thermally conductive, it's electrically conductive. For us, and really kind of in the DNA of what it means to be a professor doing applied research at Georgia Tech, we've focused on tackling those challenges to making that material practical. Because no matter what, if you want to build something at the atomic scale, everything eventually has to interface at the scale of humans because you're selling it to people. So you have to figure out ways to build systems around these small things. And that's really kind of the exciting thing behind nanotechnology specifically in carbon nanotubes, but also what we do in the Nest Lab at Georgia Tech.
And so if I had a carbon nanotube in my hand and I touched it against something that was hot, you're saying that the rate at which the heat would move into the carbon, the heat would be absorbed by the carbon nanotube. It itself is either much more efficient than anything else we've got, but it makes some really good trade-offs on how it absorbs heat. I think I have that right.
If you had it as a straw, you could think of, so the carbon nanotube is about 10,000 times smaller in diameter than the human hair. But the record is the order of an inch long that you can grow a single one. So you could take that inch nanotube and the heat from your fingers, if you just took it like a straw and put it on a piece of ice, was almost instantaneously melt that ice where it touches.
And so then the idea, and so the way that you characterize, it's not just heat at a big scale. It's you got to start at heat at the very smallest scale. The individual devices, in a circuit on a chip, in a computer or something like that. And so do you envision kind of those nanotubes as sitting adjacent to or on those circuits on a chip, or how do you think about integrating these carbon nanotubes, say, into a current system?
That's a really good question, Steve, because when I started as a researcher, as a student, a lot of people were talking about ways to integrate by fabricating these materials onto existing computer chips and things like that. But there are always these trade-offs. And so these materials require high temperature to be grown with good properties. So to some degree, you have to figure out how to solve that puzzle. And that's really where Carbice, my startup company, comes in, is that we figured out a way to deliver the material to applications, whether computer chips or other things, without having to fabricate them directly there. And we do it really through an adhesive technology that we invented at Georgia Tech and licensed to the company that allows you to, at the molecular scale, bond an individual nanotube in an array of trillions of them to a surface, and really to do it over multiple surfaces. And so that was actually the light bulb, if you will, that went off in my mind as a faculty member, that we had solved a really big problem that was holding up the commercialization of that technology.
And so where it just seems like there's such a huge number of ways. So given now you can kind of stick these carbon nanotubes on other things, that makes tons and tons of sense that you could get the heat off of them quicker and more efficient. So but it seems like it would apply to tons of different things. And so I'm really curious about where you're applying it, what carb ice is, where do they see this, the first and best applications for it?
The first thing to know about commercialization of a materials company is everybody's excited, but everybody's also scared of it, in the sense that it's very risky for an Intel or Qualcomm or some big company to immediately take a new technology into their production fab. So you kind of start in steps. And for our company, we started with the commercial space market with satellites. So telecom satellites, radio, internet, these things coming down from space now, these are the places where a material like ours enables them to hit new standards of performance. And, they're risk takers. Anybody that sends anything to space or goes to space is a risk taker. And so once people like that take on, then you kind of take the next step, and we use our product in the semiconductor fabrication facility. It doesn't actually go into the final product because they're not quite ready for that step yet. But the tools that they use to qualify, to do reliability tests, where they have to actually power up devices before they sell them, require water-cooled heat sinks because they dissipate so much power. But you can imagine they can't have a heat sink for every device they make. So they need heat sinks that can touch many devices and kind of come down and engage and disengage. So our material, being that it's so durable, these carbon nanotube-based technologies have a lot of strength, that it can last millions of insertion cycles. So those are the two places you can find our technology today. In 2020, we'll probably have some new technologies in consumer electronics. Those are emerging. It's a process. And so to your point about the versatility of that application approach, it really doesn't even have to be heat dissipation. There's so many applications in electrical connection, in mechanical energy absorption, that take advantage of the same platform. And kind of what you want to do, and I think the best sweet spot to be in is to kind of start with a material platform that's universal, and then focus in on one particular aspect that's interesting, like we did with thermal, just to get it out there.
I'm going to change gears a little bit and brag on your behalf about one of the awards. You've received so many awards for the research that you've done and many other things. And one of the awards that you received in the last year or two is something called the Waterman Award, which I think most people characterize as the top award in science and engineering for someone, in the middle of their career, period, in the entire country. And you were the winner of that. And so can you say a little bit about, what that award is and what it means to you, and then how it's a big deal. It's bigger than a big deal. And it must have had some impact on you personally, impact on your career, and kind of and continue to guide you. So I'm curious about saying a little bit about that award and what it's meant, and where you headed.
It's a big deal. Yeah, I think it's quite, I want to say humbling, but I think it actually drives a lot of perspective for me. I think that it's not something that I thought of when I started my career. And I think the perspective is that the way that I started my career, actually, it was important. When I went to the Waterman, I had my parents, my in-laws, my wife, my PhD advisor. It was a special time to have everybody kind of come up there and participate in that with me. And when I gave my acceptance speech, I kind of talked about the beginning of my career when really all I really wanted to do was to do something that was going to be impactful. And that was kind of the focus. And I wanted it to be a challenge such that if I achieved it, then it would be a significant thing. But if I didn't, I would learn a lot in the process. And so for everything to have actually worked out like I planned in a 3-month period when I really didn't know what I was doing, gave perspective because it wasn't easy. It took a lot of false starts, and I've reflected back on probably the 5 or 6 times that I wanted to give certain projects up. That to have it work out like that was just a special thing. And to be frank, it was a special responsibility that I felt to do something really important with that honor, to come back to Georgia Tech and to try to, it comes with $1 million. So, for those listening, it's a lot of money, no overhead, all these, this is like a true $1 million. And I think I set the record for being the Waterman Award winner to spend his money the fastest. And I did that by investing in what is the largest carbon nanotube reactor, I think, at any university in our country, that's now set up in our Pettit clean room. And it's now working. And it's going to be capable of putting out more carbon nanotube material than Georgia Tech's probably ever put out in its history in a month. And I did that because for my experience at Georgia Tech to enable me to have an opportunity to be honored like that, I want to put Georgia Tech on the map for this area of research, that I was honored for. And I think to do that, it's kind of a triangle. It was the research that led the Waterman and kind of getting a level of academic prestige. It's the entrepreneurship, getting a company that can commercialize and be relevant in the market. And it's the center of excellence around collaboration and bringing other people to the table to work around that. So that's it's a long explanation. I mean, I think that it would be very difficult for me to put all the emotions that I experienced in that Waterman moment, on tape. But it drove a lot of perspective. It made me reflect on my entire life and kind of the different challenges and things, and how I could tell a narrative for myself of how those things led to that moment.
Mm-hmm. It's funny, as you were talking, I was kind of I had this vision of all the things that we've talked about, your interest in entrepreneurship, your research program, and now the things you said about I have this common thread of I'm not really sure quite where I'm going when I start, but I'm going to go out, I'm going to talk to people, I'm going to, whether it's the company, whether it's the research, and they all have led to great things.
Absolutely.
And to me, that's extraordinary for our students to hear. It's not what are you going to be, it's what are you going to do. What are you going to do is going to get you to what are you going to be. And
be curious. Right? And let people help you. I think that's something that's kind of hard sometimes for technical-minded people. But I've been good at that because maybe it's because I'm the youngest of 3 children, and you kind of just learn how to survive in an environment. But I'm there's a humility to it, to be able to be open to being vulnerable to someone else and your experience, depending on what they will share with you or give with you, right? I think that's a part of, frankly, all the big work, big science that I've done has resulted from that. And I think that's absolutely something that our undergrads can do. And I think that's absolutely a transition that I saw in Startup Lab through the CreateX curriculum, that these students became more comfortable letting other people guide them to wherever they're going next.